Swayam Prabha. Digital India. Educated India.
So, welcome to this tutorial of thermodynamics. So, we are continuing the tutorial on vapor power cycles. In the previous tutorial, we solved ideal Rankine cycle, and we had some theoretical discussion also. So, we will continue the discussion, but today from the previous problem that we solved in the previous tutorial, we will continue this further. So, this is the problem that we have solved here. Basically, we considered a simple ideal Rankine cycle that produces a net power output of 45 megawatt, and these are the conditions that is given. We already solved this problem. Now, we will continue this problem further, and now what we are interested in second law analysis, right. So, all the other parameters remain the same. Now, we have to determine the exergy destruction associated with the heat rejection process. Now, 421 is the heat rejection process. Okay. So, we have to calculate the exergy destruction during this heat rejection. Also, we have to determine the exergy of the steam at the boiler exit. So, this is the exit of the boiler, point 3. So, there we have to calculate what is the exergy destruction. Okay. So, let us begin this problem. So, what we have to do, we are continuing the previous problem only, but here first we are going to calculate the exergy destruction during the heat rejection process. So, we already know that S1 is basically the enthalpy of the saturated water at 10 kilopascal, okay, that is the condenser pressure, and S1 is basically equal to S2, right, and that should be equal to 0.6492 kilojoule per kg Kelvin. Okay. This you can get from the stream table. Now, also S3 is equal to S4, right. So, from the previous solution, you know S3, that is basically 6.8 kilojoule per kg Kelvin, and that is basically equal to S4. Now, you also know what is the enthalpy corresponding to the state 3, and that we already obtained as 3411.4 kilojoule per kg Kelvin, kilojoule per kg. Okay, this is enthalpy. We in the previous tutorial we already calculated what is the heat rejection Q out, and that this Q out we calculated as 1961.8 kilojoule per kg. Please refer to the previous solution and then you will get this basically. Now, we need to calculate the exergy destruction during process 421. Okay. So, that should be equal to T naught times S out, that is basically the final state, that is 1, minus initial state, that is 4, okay, and you have to add the heat rejection basically. So, Q out during this process 421, that is heat is rejected, and that temperature of the sink, that is given as 290 Kelvin, okay, in this problem. Okay. So, this is 290 Kelvin. So, let me write it as temperature of the sink. Okay. So, now you substitute the numbers. So, this T naught is basically the temperature of the surrounding, that is 290 Kelvin, and S1 we already obtained as 0.6492, S4 is 6.8, and then you have to add the heat rejection, that is Q out 1961.8 divided by 290. So, if you obtain, then you will calculate it as 178 kilojoule per kg. Okay. So, that is the exergy destroyed during process 421. Now, we need to calculate the exergy of the steam at the boiler exit. So, we have to use this formula, and psi 3, that can be written as H3 minus H naught, right, because we are evaluating point 3, and H naught is the surrounding. Okay. So, the exergy at point 3 is basically equal to the enthalpy difference between the point 3 and the surrounding, and then you have to add you have to subtract T naught multiplied by S 3 minus S naught. So, that is the exergy. Another contribution will come from the change in the kinetic energy, okay, and change in the potential energy. Let us say V 3 square by 2 plus G Z 3. So, neglecting the changes in the neglecting the change in kinetic and potential energy, you can simply write it as H 3 minus H naught minus T naught times S 3 minus S naught. Now, if you put the number H naught, you can find as enthalpy corresponding to at 290 Kelvin and corresponding to 100 kilopascal. Okay. That is basically this one. So, P naught is 100 kilopascal and the reference is basically the sink temperature, that is 290 Kelvin. So, this is nothing but enthalpy of the liquid water at 290 Kelvin. Okay. And you can write it as 71.95 kilojoule per kg. So, this is the H naught. Now, you have to also know what is S naught. Okay. So, S naught similarly you can write it as SF at 290 Kelvin, and that is equal to 0.2533 kilojoule per kg Kelvin. Okay. So, now you plug in the number here. So, H 3 is 3411.4, H naught is 71.95 minus T naught is 290 times S 3 is 6.8 and S naught is 0.2533. So, you calculate this as 1440.9 kilojoule per kg. So, that is the exergy of the steam at the boiler exit. So, now I will move to the next problem. So, before moving to the next problem, let us discuss this. How do the following quantities change when a simple ideal Rankine cycle is modified with reheating? Okay. So, yesterday in the previous tutorial you have seen that simple ideal Rankine cycle. Now, if you modify that for reheating, then how these parameters change. Okay. Assume the mass flow rate remains the same. So, here again I will draw the TS diagram and explain it. So, so 1 to 2 is basically your pump work, and then 2 to 3 is your this thing boiler. Okay. So, heat addition in the boiler Q in. Now, 3 to 4 is your expansion in the turbine. So, now if you modify this for reheating, then what will happen? Suppose you expand from 3 to, let us say another point which is 3 dash, okay, or maybe here 3 dash, and then you again heat it up to another high pressure, another high temperature. So, let us say this is your heat addition, again second round of heat addition. Now, you expand it further. Okay. Let me redraw this. So, 1 to 2 is the pump work, 2 to 3 is the boiler heat addition Q in, 3 to 4 is expansion in the turbine, and 4 to 1 is the heat rejection. Okay. So, now if you modify this for reheating, then let us say you take a point here and then you take it up and then you expand. Okay. So, then this will be the modified cycle. So, 3 to 3 dash is the expansion in the first stage of turbine, then you are taking it to another point, let us say 3 double dash, and then you are expanding it to 4 dash. Okay. So, that is the process in the reheating cycle. Now, what will happen to these quantities? So, if you see in this reheat cycle, there are 2 turbines. So, first turbine is basically 3 to 3 dash, and then the second is 3 double dash to 4 dash. Okay. So, I should have put the arrow right. So, what will happen to the pump work input? Pump work input is basically 1 to 2, which will remain the same. Okay. That will not change. Now, what will happen to the moisture content? So, as you can see that the moisture content, I mean you know that dryness fraction for 0.4 dash is more than dryness fraction of 0.4. Therefore, the moisture content at the turbine exit will decrease. Okay. So, it will have less amount of liquid water. What will happen to the heat supplied? So, heat supplied now will become 2 to 3, and then you have to add 3 dash to 3 double dash, right. So, there is more heat addition. So, heat supplied will increase. What will happen to the heat rejection? Heat rejection will also increase, because the area under the curve 4 dash to 1 is basically the heat rejection now, and earlier it was this much 4 to 1. Okay. So, you can see that the heat rejection will also increase. What will happen to the turbine work output? Turbine work output initially it was 3 to 4, basically originally it was H3 minus H4, now it will become H3 minus H3 prime, then H3 double prime minus H4 prime. Okay. So, you can basically see that the turbine work output from this figure, you can see that it increases. Okay. So, next we will move to a quantitative problem. So, here we are considering an ideal reheat Rankine cycle, which uses water as the working fluid, and it operates operates the inlet of the high pressure turbine at 8000 kilopascal and 450 degree centigrade. Okay. So, let me first draw the TS diagram. So, 1 to 2 is the pump, 2 to 3 is the first I mean heat addition in the boiler, then 3 to 4 is the expansion in the first turbine. So, let me draw up to this within the vapor dome. I am not sure whether it will be inside the vapor dome or outside in the superheated region, but just for the sake of illustration I am drawing 3 to 4 is the expansion in the first turbine, then 4 to 5 is again heat addition in the boiler, then you expand it to 0.6. Okay. Okay, you expand it to 0.6, and then from 0.6 you reject the heat and come to 0.1, and from 1 you go to 0.2. Okay. So, this is the cycle, okay, that we are considering. Now, what is given? Inlet temperature of the high pressure turbine, which is basically 0.3, it is given. So, T3 is 450 degree centigrade, and P3 the pressure is 8000 kilopascal. Okay, that is given. Now, correspondingly you can find from the superheated steam table, H3 is 3273.3 kilojoule per kg, and S3 is 6.5579 kilojoule per kg Kelvin. So, I am not writing the unit for the sake of time, but you should always write this in the exam or otherwise. Okay. Now, what is happening here? The inlet of the low pressure turbine is given, that is 500 kilopascal. So, this is your basically 500 kilopascal. If I draw a constant pressure line, this is your 8000 kilopascal, and the condenser pressure is given, that is 10 kilopascal. Okay. And temperature corresponding to this inlet of the second turbine, that is the low pressure turbine, is 500 degree centigrade. So, what is given, T5 is 500 degree centigrade. So, after reheating it becomes 500 degree centigrade, and P5 is basically equal to P4, that is 500 kilopascal. So, now again we can find these things from the superheated vapor table. H5 is 3484.5 and S5 is 8.0893. Next, I will try to calculate the properties of point 1 and 2. So, H1 is pretty straightforward. H1 is enthalpy of the saturated liquid water at 10 kilopascal, and that can be found from the table as 191.81 kilojoule per kg. And we can also find the specific volume corresponding to this, and specific volume can be obtained is 0.001010 meter cube per kg. Okay, that is the specific volume corresponding to 0.1. Next, we can find what is the pump work. Pump work is basically V1 multiplied by the change in pressure, that is P2 minus P1. Now, P2 is basically 8000 kilopascal and P1 is 10 kilopascal, okay, and V1 is also written here. So, you can calculate the pump work in, and this will come out as 8.07 kilojoule per kg. Now, we can find the enthalpy corresponding to this point 2. Here H2 will be H1 plus the pump work, and if you add these things you will get it as 199.88 kilojoule per kg. So, that is the enthalpy of point 2. Okay. Now, let us try to find the point 4 here. So, after the first stage of expansion in the high pressure turbine, you know, this is an ideal Rankine reheat Rankine cycle. So, basically S3 will be equal to S4. Okay. Now, S3 is this much, 6.5579 kilojoule per kg Kelvin, that should be equal to SF plus X4 multiplied by SFG. Okay. So, if you now look at the stream table, you will see that this point 4 will be within the vapor dome, and therefore, you have to calculate the dryness fraction of point 4. Okay. So, from this expression you have to substitute the value of SF and SFG. So, corresponding to this 500 kilopascal enthalpy of the saturated liquid water, that is basically 1.8609, 1.8604, and X4 is the unknown, and SFG is basically 4.9603, and S3 we have already written as 6.5579. So, from this we can calculate what is X4, and X4 you will get it as 0.947. So, that is the dryness fraction for point 4. Now, next is the enthalpy for point 4, that will be HF plus X4 HFG. So, now enthalpy of saturated water is 640.09 plus 0.947 times HFG is 2108. So, you will calculate it as 2636.4 kilojoule per kg. Okay. So, next we have to find what is the point 6. Okay. So, similar way you can find what is the enthalpy for the point 6, because you know S5 is 8.0893 and S5 will be equal to S6. So, from that you can find what is the dryness fraction for point 6. Okay. So, I am not repeating this, I will just write the dryness fraction X6 and is 0.9921. You have to calculate it following this previous process, and correspondingly you can find H6 as 64.9 kilojoule per kg. Next we have to calculate the mass flow rate through the boiler, okay, needed to produce a net power of 5 megawatt, right. So, what is the mass flow rate of steam that we have to find, and thermal efficiency of the cycle. So, these are the things. So, one is the mass flow rate of the steam, another is the thermal efficiency of the cycle. So, let us first calculate what is the heat addition. So, Q in is the heat addition, that should be equal to H3 minus H2, that is the first stage of heat addition, and the second stage of heat addition is H5 minus H4. So, you just put the numbers and you will calculate this as 3921.5 kilojoule per kg. Now, what is Q out? Q out is basically H6 minus H1, and that can be calculated as 2373.1 kilojoule per kg. Now, you can calculate the efficiency of the cycle easily. So, it will be 1 minus Q out upon Q in, and if you plug in the number, the efficiency will be 39.5%. Okay. What remains is the mass flow rate of the steam. So, basically it produces 5000 kilowatt. So, W dot is basically 5000 kilowatt. So, that should be equal to m dot steam, that unit is kg per second, multiplied by net work output of the cycle. So, W net. So, net work output will be in kilojoule per kg. Now, we can calculate the net work output. So, W net is nothing but the heat supplied minus heat rejected, and then if you plug in the number, it will be 1548.5 kilojoule per kg. So, now you know everything except m dot s. So, m dot s can be calculated as 5000 kilowatt is kilojoule per second divided by W net, which is 1548.5 kilojoule per kg. So, this will give you 3.229 kg per second. So, that is the rate of flow of water in the boiler. Okay. So, this brings us to the end of this problem. We will continue this problem, and in the second part we will see that which component of the ideal reheat Rankine cycle offers the greatest opportunity to regain lost power potential. Okay. So, we have to assume that sink temperature as 10 degree centigrade or 283 Kelvin, and the source temperature, this is the source temperature, or that is basically, or I should write T source. T source is 600 degree centigrade or 873 Kelvin, and this is basically the sink temperature. Okay. So, all the parameters remain the same of the previous problem. So, we need to calculate which component, we have to identify that which component of the ideal reheat Rankine cycle offers the greatest opportunity to regain lost power potential. So, what we have to do? We have to calculate the exergy destroyed during different processes. So, exergy destroyed is nothing but T naught multiplied by the entropy generated. So, T naught and entropy generated will be that entropy at the exit minus entropy at the inlet, and then you have to subtract heat addition divided by the source temperature plus heat rejection by the sink temperature. So, this is a general expression which we have already seen in the previous class. So, you have to use this to obtain the exergy destroyed during different processes. Now, what are the processes? Let me refer to this TS diagram. Here you can see that process 1 to 2 is an isentropic process, process 3 to 4 is again an isentropic process, and process 5 to 6 is again an isentropic process. Okay. So, therefore, these three processes, I mean there is exergy destruction in these processes will be 0, right. Okay. because 1 to 2, 3 to 4 and 5 to 6, these three processes are isentropic process or reversible adiabatic process. So, here the exergy destruction will be equal to 0, because if you look at the formula here, exergy destroyed is nothing but the difference in the enthalpy. So, difference in enthalpy, that is delta S across 1 to 2, that is in the pump, and the 3 to 4, that is in the turbine, and 5 to 6 again in the turbine, delta S is basically 0, and there is no heat loss from the turbines and the pump or heat addition. Okay. Therefore, the exergy destruction in these processes will be 0. Now, we turn back our attention to the process 2-3. So, exergy destruction during process 2 to 3, that is the heat addition in the boiler. Let us try to calculate this. So, that should be equal to T naught. So, T naught is 283 Kelvin, right, multiplied by AC minus SI. So, AC is the exit temperature. So, that will be the temperature of S3, right, and this is S2. Okay. Now, during 2 to 3 process there is heat addition. Okay. So, therefore, this heat addition has to be accounted, and the source temperature is T source. I will just substitute later. Okay. So, this is the exergy destroyed, and that should be equal to 283, and S3 we already found as 6.5579, S2 we found as 0.6492, and heat addition is that we calculated is as 3073.4, and the source temperature is 873 Kelvin, right, 600 degree centigrade, right. So, it is 873 Kelvin. So, now you can calculate exergy destroyed during this process 2 to 3, and it comes out to be 687.1 kilojoule per kg. Okay. So, that is the exergy destroyed during the heat addition between process 2 to 3. Okay. So, next I will move to process 4 to 5, that is again another heat addition during the reheating. So, during 4 to 5, so T naught is, so it will be T naught multiplied by S5, that is the end point, minus S4, again heat is supplied. So, Q in divided by the T source. So, if I plug in the number, it is 283, S5 is 8.0893, S4 is 6.5579, and heat addition here is 848.1 kilojoule per kg, and source temperature is 873 Kelvin. So, you calculate exergy destroyed during process 4 to 5 as 161.6 kilojoule per kg. Next, I will look at the heat rejection step, that is 6 to 1. Here it will be T naught S1 minus S6. So, S1 is the final state and S6 is the inlet, and here there is no heat addition, but there is heat rejection. So, Q out divided by the T sink. Now, T naught is basically 283 Kelvin. So, 283 S1 we obtained as 0.6492, S6 is 8.0893, and heat rejection is 2373.1 kilojoule per kg divided by the sink temperature, that is 283 again. So, you calculate this as 267.6 kilojoule per kg. So, what we can see from this problem of ideal reheat Rankine cycle, that exergy is destroyed during the heat transfer processes. So, during the heat addition in the boiler, both in the first phase and during the reheat, and during the heat rejection in the condenser, we see that there is an exergy destruction. During the isentropic processes, for example, the pump work and the expansion in the turbine, we see that the exergy destruction is basically 0 for this ideal case. Now, when there is some internal reversibility, for example, there is, we consider the friction in the pump and the turbine, then there could be some exergy destruction, because then delta S during that expansion process in the turbine will not be equal to 0. Okay. So, therefore, if we are considering an actual Rankine cycle, then there will be exergy destroyed during the turbine expansion and the pump compression. Okay. So, this brings us to the next problem. So, here first we will discuss this, how do the following quantities change when the simple ideal Rankine cycle is modified with regeneration. Okay. So, here we have to assume the mass flow rate through the boiler is the same. So, what I will draw, I will basically draw a simple I mean an ideal Rankine cycle with regeneration, and then we can try to answer this. So, first I will draw the TS diagram. So, here let us say one to 2 is the pump work, then you have 2 to 3 2 to 3 is basically the regeneration here, and here what you are doing, that you are taking some of the steam from this point, let us say here, and you are mixing it with the water at point 2. Okay. So, what you get is this, and then next you again put it in a pump and pressurize it to this point, and then there is a boiler for the heat addition. Okay. So, this is the TS diagram for an open feed water heater, right. So, open feed water heater, you basically mix the condensate after pressurizing it, and then you mix the blade steam, okay, and then you bring it up to this point 3, and then you again use another pump to pressurize it to point 4. Okay. So, this is the TS diagram for an open feed water heater. Now, let us try to answer these questions. So, what you can see here, that in this problem the moisture content remains the same at the exit of the turbine, because the you can see that the 0.7 has not moved. So, the moisture content remains the same. Okay. And what about the other things, for example, heat rejection? Heat rejection here will decrease, because here the heat is rejected between process 7 to 1, but here some amount of steam, let us say y amount of steam you have already taken for regeneration purpose. So, only 1 minus y amount of steam will be here in the condenser. Okay. So, therefore, the heat rejection will be 1 minus y multiplied by H7 minus H1. So, that is the heat rejection in the condenser, okay, which is less than H7 minus H1. So, that was the original heat rejection. So, you see that the boiler the heat rejection will decrease. What will happen to the heat supplied? So, here the heat is supplied between 0.4 to 5. Okay. Earlier, if there is no regeneration, then you would have supplied heat from 0.2 to 5. So, again you can see that the area under the curve 4 to 5 is small compared to the area under the curve 2 to 5. Therefore, the heat supplied will also decrease. Now, what will happen to the turbine work output? Turbine work output, if you see that the specific work output is basically H5 minus H7, which is same for the both the cases. But here if you see that the difference H5 minus H7 is the same, but in the original cycle H5 minus H5 minus H7 is the turbine work. Okay. Now, in the new case W dash T, that new work done with regeneration, it will become H5 minus H6 okay, plus 1 minus y, because 6 to 7 only 1 minus y kg of steam is basically getting expanded. Okay. So, it is 1 minus y multiplied by H6 minus H7. So, you can see that the turbine work output will also decrease due to regeneration. Okay. So, this is the answer of this question. So, hopefully, it is clear to all of you. In the original case, H5 minus H7 is the specific work done by the turbine, but in the Rankine cycle with regeneration, H5 minus H6 times 1 kg, okay, is the work done up to 0.6, and then from 0.6 to 7 only 1 minus y kg of steam is basically getting expanded. So, therefore, your specific work done will decrease, right. So, that is how the turbine work output decreases. So, next I will move to a numerical problem. So, this is a regenerative Rankine cycle, and it is an ideal cycle. Steam enters the turbine at 6 megapascal and 450 degree centigrade. So, basically T3 is 450 degree centigrade and P3 is 6 megapascal, okay, and it is condensed in the condenser at 20 kilopascal. Steam is extracted from the turbine at 0.4 megapascal to heat the feed water in an open feed water heater. Okay. So, if I draw the diagram, then it will look like this. So, first I will draw the TS diagram. So, 1 to 2 is basically the pump work, 2 to 3 is the regeneration, heating of the condensate up to the saturated liquid temperature, and then so let me draw it again. So, I will start with this 0.5, which is the turbine inlet temperature, turbine inlet. So, T5 is 450 and P5 is 6 megapascal. So, from 5 I am expanding it to up to 0.7. Okay. So, here 7 to 1 is basically the heat rejection in the condenser, 1 to 2 is basically the pump work, and then you are taking some of the steam at the from 0.6. We do not know whether the 0.6 will lie inside the vapor dome or the outside vapor dome, but let us say I am drawing it like this, and later we will see that where the point lies. So, we are taking out steam and then we are mixing it with this steam available at 0.2, and then this will bring us to 0.3. So, in an ideal regenerative cycle with open feed water heater, the objective is that you heat up the condensate after the pump up to the saturated water temperature. So, basically let us say I am extracting y kg of steam from this and I am mixing with the pumped water, and then I am taking the temperature of the water up to the saturated liquid. I mean I am taking the temperature up to this 0.3. Now, from 3 to 4 there is a pump, and from 4 to 5 there is heat addition in the boiler. Okay. So, that is the cycle diagram of an open feed water heater. Okay. So, what is given in the problem? T5, that is the turbine inlet condition, as 450 degree centigrade, and P5 is 6 megapascal. So, for this I can find what are the values of enthalpy and entropy. So, from the superheated table you can find it as 3302.9 kilojoule per kg, and S5 is 6.7219 kilojoule per kg. Okay. Now, steam is let us start with point 1. So, point 1 enthalpy we can find it as enthalpy of saturated water at 20 kilopascal. So, this is the 20 kilopascal constant pressure process, and this line is 6 megapascal, and steam is extracted at 0.4 megapascal. So, let us say y kg of steam is bled, and here 1 minus y kg is going through the condenser. So, enthalpy corresponding to 20 kilopascal, enthalpy of saturated water is 251.42 kilojoule per kg. Now, you can find out the enthalpy at point 2. Okay. I am not going through the exact solution of this, I will just write down the answer, and you can follow how to obtain this point H2 from the previous problem. So, enthalpy of point 2 is 251.81 kilojoule per kg. So, it is very simple. So, what you have to find is the specific volume corresponding to point 1, and then you have to multiply it with P2 minus P1, that is the pressure difference. So, P2 is basically 0.4 megapascal and P1 is 20 kilopascal. So, you have to take it, you have to multiply this, and then you have to add H1, then that is basically H2. Okay. So, I will not do all these steps here because of the lack of time, but the process I have already described several times. So, you can follow it. Now, for point 3 I know that it is 0.4 megapascal, and correspondingly I can find enthalpy of point 3 as enthalpy of saturated water at 0.4 megapascal, that is nothing but 604.66 kilojoule per kg. That is the enthalpy for point 3. Now, I can find what is the enthalpy of point 4. So, H4 will be H3 plus the pump work, right. So, pump work will be V3 multiplied by 6 megapascal or 6000 kilopascal minus 0.4 megapascal or 400 kilopascal. Okay. So, this is your 6 megapascal, that is P4, and this is your 400 megapascal, that is P3, right. So, you can calculate this. So, enthalpy of point 4 you obtain as 610.73 kilojoule per kg. Okay. Now, what remains is enthalpy of point 6 and enthalpy of point 7. So, it is an ideal cycle. So, there is no the expansion process in the turbine is isentropic. So, we know entropy of 0.5 S5 and S6 will be basically equal to S5, and S6 if you look at the vapor, if you look at the steam table, you will see that this 0.6 will lie inside the vapor dome, because at 0.4 megapascal you will see that the Sg, that is the entropy of the saturated vapor will be less than will be more than this value of S6, right. So, enthalpy of saturated entropy of the saturated vapor at 0.4 megapascal will be greater than entropy of S6. So, S6 is how much? S6 is 6.7219. Okay. So, therefore, this point will lie within the vapor dome, and we have to calculate the dryness fraction. So, that will be SF plus X6 multiplied by SFJ. Okay. So, from this you can calculate X6. So, you have to find SF and SFG for saturation pressure of 0.4 megapascal. Okay. For 0.4 megapascal you have to find these numbers, and then you can calculate X6. So, I am not writing all the values, that you can do at home and it will help you to practice, and X6 is 0.9661, and correspondingly you can find H6 HF plus X6 into HFG, and H6 you can calculate as 2665.7 kilojoule per kg, that is the enthalpy of 0.6. In a similar manner you can also find enthalpy of 0.7. Okay. What you have to do, you have to equate entropy of 0.5 to entropy of 0.7, then you can calculate the Dyna's fraction of 0.7, and using the Dyna's fraction you can evaluate enthalpy of 0.7. So, H7 you can find similarly, and the answer will be 2214 kilojoule per kg. Okay. Now, what are the questions that we have to answer? The net work output per kilogram of steam flowing through the boiler. So, basically the specific work output of this. Okay. And we have to, so basically W net, and we have to calculate the thermal efficiency of the cycle. Okay. So, what is remaining is the energy balance in the across the feed water heater, because unless we know how much amount of steam is bled, we cannot calculate the net work output and the efficiency of the cycle. So, we have to do an energy balance across the feed water heater. Okay. So, we are assuming that the change in kinetic energy and also change in potential energy is negligible, and therefore, whatever energy is going in minus energy out, that should be equal to the delta E of the system, right. So, that is the energy equation that we have to apply, and this change in energy of the system should be 0 because it is a steady state process. So, this gives us energy in should be equal to energy out. Okay. Now, if you consider the feed water heater, so what is happening here? So, you are taking out steam from 0.6 and then mixing with the water at 0.2, and finally it is coming out at 0.3. Okay. So, if I draw a diagram, so here you are supplying water at an enthalpy H2 and you are mixing steam, which is basically a two phase mixture at an enthalpy of H6, okay, and then you are getting H3. Okay. So, here you are taking y kg, okay, and here it is 1 minus y kg, and here what is coming out is 1 kg. Okay. So, this is an open feed water heater. So, you are mixing the condensate with the water at 0.2 and you are getting the 0.3 here. Okay. So, now from this energy balance you can calculate what is the value of y. So, energy in should be equal to energy out from the first law of thermodynamics, and now if I write it as in terms of the what is the energy that is going into the system is basically m dot 6 multiplied by H6, that is one stream, and the second stream is m dot 2 multiplied by H2, and what is coming out is m dot 3 H3, right. Now, what is m dot 6? M dot 6 is y kg, okay, multiplied by H6, and m dot 2 is 1 minus y kg multiplied by H2, that should be equal to m dot 3 is 1 kg multiplied by H3. So, it is H3. So, from this we can calculate y, and y will be H3 minus H2 upon H6 minus H2. So, you put in the number 604.66 minus 251.81 divided by 2665.7 minus 251.81. So, the answer will be 0.1462. So, this much kg of condensate will take out from the turbine and will mix with the feed water. Okay. So, this much kg per kg of total flow of water. Okay. So, next we have to calculate what is the net work output of the system. So, for that first I will calculate what is Q in. Q in is basically the energy heat addition during process 4 to 5. Okay. So, Q in is H4 minus H5 and Q out is basically 1 minus Y kg H7 minus H1. So, these are all the heat addition and heat rejection per kg of mass flow. Okay. So, H4 minus H5. So, if you put in the number, you will get it as heat addition will be H5 minus H4, right. 5 is the final point and 4 is the initial point. So, H5 minus H4 is 2692.2 kilojoule per kg. So, this is the specific heat addition and Q out will be 1675.7 kilojoule per kg. Okay. So, now you can calculate what is the net work output. Net work output will be Q in minus Q out, and that is 1016.5 kilojoule per kg, and the thermal efficiency will be 1 minus Q out upon Q in, or basically W net upon Q in, and you can calculate this number as 37.8%. So, that will be the efficiency of this ideal regenerative cycle. So, this brings us to the end of this problem. In the next problem, we are going to look into quickly a regenerative Rankine cycle with closed feed water heater. So, here it was an open feed water heater, but now we are looking into a closed feed water heater. Okay. So, here what is happening, in the closed feed water heater, regenerative Rankine cycle is to heat 7000 kilopascal feed water from 260 degree centigrade to a saturated liquid. If I draw the heater, so let us say, so this is the closed feed water heater. So, in the open feed water heater, condensate and feed water mixes together directly, okay, and comes out as a single stream, whereas in the closed feed water heater they remain as a separate stream. So, basically one stream is the feed water, okay, that enters, let us say this is station 1, and then it comes out to station 2, okay, and steam is bled from the turbine and that is supplied, let us say at point 3, and then it comes out at point 4. Okay. Now, this feed water is already pressurized and it is at a higher pressure. So, therefore, you have to use a pump here, okay, and from the pump whatever I mean this liquid will be transferred to the this point. Okay. So, this is station 2 and now they will mix and come out as, let us say, so this is station 5 and this is station 6. Okay. So, one line is basically the feed water. So, feed water is flowing from this point 1 and it comes out like this, okay, and another is basically the steam which is coming like this and comes out of this feed water heater, and here in the state 4 it will be basically a liquid state, saturated liquid state, and then you can pump it to a higher pressure, let us say 5, and then you mix these 2 points. So, both these 2 and 5 will be at the same pressure, then you can mix it and they will come out as 0.6. So, that is the concept of closed feed water heater. Now, let us look into this problem. What is given is that P1, that is 7000 kilopascal, and T1 is 260 degree centigrade. What is given is P3, that is the condition of the steam, that is 6000 kilopascal and T3 is 325 degree centigrade, right. And the condition of 0.6 is also given, it is saturated liquid at 260 degree centigrade, right. So, P6 is basically 7000 kilopascal, right. There is no pressure drop in ideal case, and here X is equal to 0, right. It is a saturated liquid. So, now correspondingly we can find what is the enthalpy. Enthalpy of 0.1 will be enthalpy of liquid water at 260 degree centigrade, which is nothing but 1134.8 kilojoule per kg. Okay. Now, for this enthalpy at H3 will be 2969.5 kilojoule per kg. Okay. And for this enthalpy at 0.6 is basically enthalpy of liquid water at 7000 kPa, and that is 1267.5 kilojoule per kg. So, these are the enthalpies. Now, again we will do the energy balance. So, energy in should be equal to energy out for a steady state system, and we are neglecting the changes in any kinetic energy and the potential energy. So, now I will do the heat energy balance across this closed feed water. So, what is coming in, let us say what is coming in. So, this there is one stream that is coming in, okay, and this stream is also coming in, okay, and what is going out is this one and this one. Okay. So, if I do the energy balance, then it will be m dot 1 H 1 that is coming in plus m dot 3 H 3 that is also coming in should be equal to m dot 2 H 2 which is going out and m dot 4 H 4 that is also going out. Okay. So, from this okay, so I will do it in a different manner. So, I will not consider this as the control volume. I will use this as a control volume, this one. So, let us say this entire thing is your control volume. Okay. So, in this control volume there is this feed water that is coming at 0.1, steam is coming at 0.3. Okay. So, I can write it as m dot 1 H 1, okay, that is coming in, and m dot 3 H 3 that is also coming in. Now, what is happening? There is some pump work. So, that is m dot 3 W p, okay, because of this pump. Okay. So, there is some pump work that is going in, and what is coming out is m dot 6, this one is coming out m dot 6 H 6. So, I have defined a control volume like this, okay, and I am now calculating all the interactions. So, one is this is the state 1. So, m dot 1 H 1 is coming in and m dot 3 H 3 is also coming in, and what is supplied here? We are supplying work done work on the pump. So, basically m dot 3 multiplied by W p is the amount of work done on the pump, that should be equal to m dot 6 times H 6. Okay. So, from this we can calculate what and then what we have to do, we have to solve for m 3, right. So, m dot 6 is m dot 6 can be written as m dot 1 plus m dot 3. Okay. So, we can solve for m dot 3 and we will get it as m dot 3 should be equal to m dot 1 multiplied by H 6 minus H 1. In the denominator it will be H 3 minus H 6 plus W p in. Okay. So, from this expression we can solve for m dot 3 and we will get this. Next I can put in the number, but for before that we will calculate what is the pump work. So, pump work will be V4 into P5 minus P4. Okay. So, this is V4, V4 is basically specific volume of liquid water at 6000 kilopascal multiplied by P5 minus P4. So, this is 0.001319 meter cube per kg multiplied by 7000 kPa minus 6000 kPa. So, this will be 1.319 kilojoule per kg. Now, you substitute this pump work here and you already know H6, H1 and H3, then you can calculate m dot 3. Okay. So, m dot 3, you also know that m dot 1 is 1 kg per 1 kg. Okay. So, basically you can calculate m dot 3. M dot 3 will be, m dot 1 is 1 kg per second and 1267.5 minus 1134.8. So, that is H6 minus H1 divided by 2969.5, which is H3 minus H6 is 1267.5 plus 1.319. Okay. So, m dot 3 you will calculate it as 0.0779 kg per second. Okay. So, that is the answer of this question. So, in this question we basically solved a closed feed water heater and we have obtained the amount of blade stream required to heat 1 kg of feed water. Okay. So, we have done an energy balance across this control volume and from that we found the amount of blade stream, that is m dot 3, that is needed to heat 1 kg of feed water, that is m dot 1 is basically 1 kg per second. Okay. So, that is the so m dot 3 is basically this one 0.0779 kg per second. So, in the next tutorial we will have a look at another tutorial problem on ideal reheat and regenerative cycle, and we will also solve for some problems on the cogeneration. Okay. Thank you for your attention.